Here we're looking at case O, which involves the application of the Poisson distribution. It is very useful if we begin with the Poisson distribution equation here. So there we have the probability that x takes on any particular value can be given by e raised to the minus lambda multiplied by lambda to the x, that's lambda to the x, all divided by x factorial. And we'll also use the recurring formula, is that if you have the previous value of p to the x, you can get the next one by multiplying by lambda and dividing by that particular value. I'll just show this in application so that you'll understand it a bit better. So let's look at part A. In part A, it's asking what's the probability that a trap set overnight will catch exactly 5. That's asking for what's the probability. What's the probability? Sorry. What is the probability that x is equal to 5? Here, we can just say that probability that x is equal to 5 is given by e to the minus, and lambda here is 4.5. E to the minus 4.5 multiplied by 4.5 raised to the 5th power, all divided by 5 factorial. And that's straightforward enough. We just need to carry out that calculation, and you'll need to be able to perform that, and when you do, you'll find that the probability that x is equal to 5 is given then by, after evaluating this, is given by 0.17083. And so we have our value, that probability that the function is exactly equal to 5. Well, in part B, we're asked what's the probability that a trap will catch at most 5 bugs. So when I say at most, what are the possibilities? It may catch 0, and it may catch 1, and it may catch 2, and it may catch 3, it may catch 4, and it may catch 5. Wow, that's a lot of work. Calculating that probability each time is going to be a bit tedious, especially with this relatively complicated formula. But we're going to use the recursion formula to simplify things, and we'll start with what's the probability that x is equal to 0. Well, that's just equal to e to the minus 4.5 times 1 divided by 1, or 0.11, sorry, I said that wrong. It's e raised to the minus 4.5, and when I worked that out on my calculator, I got 0.01111. I'm going to carry out my probabilities to 5 digits beyond the decimal point. Now, how would I get the probability of 1? I can apply this equation, or I can use the formula. I'll use the probability at 0 multiplied by lambda divided by the new x. So I'll multiply by lambda and divide by 1. Well, lambda is 4.5, so I get a probability that x is 1 equal to 0.01111 times 4.5, or 0.04999. Again, 5 digits beyond the decimal point. Now, how do I get probability that x is equal to 2? I can take the probability that x is equal to 1, multiply by lambda, and divide by 2. I get a probability that x is equal to 2 equal to 0.11248. Now I need the probability that x is equal to 3, and that's equal to the probability that x is equal to 2 times lambda divided by 3. So probability that x is equal to 3 is given by, oops, I don't know why that happened, but the answer was 0.11248 before. So now the probability that x is 3 is 0.16872. Now the probability that x is equal to 4 can be found from probability that x is equal to 3 times lambda divided by 4, and this one's still growing because lambda is 4.5, so when I take the probability at 3 and multiply by 4.5 and divide by 4, I get this answer of 0.18981. And finally, I could get the probability that x is equal to 5 by multiplying this value by 4.5 and then dividing by 5, but I've already got the answer over here for probability equals 5. Now I have all the numbers for this sequence, and I add up the value at 0, at 1, at 2, at 3, at 4, and at 5, and when I do, I get an answer equal to x is less than or equal to 5 equals 0.7029494, and that's my answer for part B of case 0.